I will talk about the skips must take the overview of the particle physics. It will start in the several terms in the standard Lagrangians, like the kinetic terms for the free fields, as by some propagations and the interaction form between the several fields, like the scalar spinors and the vector fields, and also we will be giving about the various elementary particle. A specific example of the scalar spin is the vector field, like as a cake leptons and gauge boson. And the values of both observed quantities in the particle physics using of the Feynman diagram. So there are some several terms in the particle physics in the standard Lagrangians. The first term is such a Dirac Lagrangians adjoint spin sized and there will be the covariance derivatives. All Lagrangian terms shape the Lorentz scalars, which is the invariance and the Lorentz transformation. So such a Dirac Lagrangian terms contains kinetic terms for the free spinor field, so-called the Dirac equation. There are some of the gamma matrix which makes the such adjoint spinors, the gamma means the gamma becomes the Lorentz scalar, Lorentz vectors, and all terms becomes the Lorentz scalar. And because only such a terms does not satisfy the local gauge invariance, so we introduced the gauge bosons, which is such a vector boson I mu. And if we including also such a gauge bosons term, then it is invariance from the local gauge transformation. So such a terms represent as the interaction between the gauge boson I mu and the spinor term. There are several gauge bosons and several kinds of spinor. Spinors can be represented in the Feynman diagram like that. And there will be some of the gauge bosons. And there are some several gauge bosons with the symmetric charge comes from the U1s of the high charge, RC2 of the isospin or Pauli matrix, and RC3 large charge represented in the gamma matrix. And the associated gauge bosons is the B mu bosons, W mu bosons, and the gluon. There will be some the coupling G1, C2, G3, including the covariance derivatives d mu. Our next possible interaction terms is kinetic terms for the scalar fields, also such a partial derivatives are replaced in the covariance derivative. So such a partial measure of the spinor is represented as the Klein-Gordon equations, which is the equation of motion for the free scalar field. And because of the covariance derivatives, there will be some coupling between the gauge bosons and scalar fields. And if scalar fields have some back-mix fluctuation value, then there will be some gauge boson equal to the mass, and small fluctuation such X phase make the interaction between the gauge bosons and scalar P. And the next possible terms is scalar potential, which contains mass terms of the scalar P's and the self interaction of scalar P's. And such a scalar potential determines the number of economic fluctuation values of the scalar P, which is a minimum point of the potential. And the next possible interactions through kinetic terms is the construct by the Weierstrass F mu. F mu is defined as commutates to the partial derivatives and the A mu. And if we insert the kinetic terms into the Euler Lagrangian equation, then we can determine the Maxwell equations for the which is some propagations of the free vector P. And the binary possible interaction terms equal interaction. One scalar P, this is spinor P, interact like that. There are spinor P's and interacting with other scalar P's. And if there are some fluctuation values for those scalar P's, and the variance equal to the mass. Also, such equal interaction is the interaction between the spinor P's and scalar P. There are some of the several kinds of the scalar spinors and vector field in standard model. The first of all, scalar fields are represented as pi. Example is Higgs especially as written as a complex colopis. So there are also AC1, AC2, and some combination of the one of the two. The second spin-off piece, which is the fermions, or elementary particles, which is the constituents of the composite particles, are the fermions. There are some of the cakes and the leptons, which is the cakes are interact via the strong interactions and gluons because they have some color charge. So it can make the composite particles, and because of the color confinement into the diffusion properties of the KCD, such as cake is always the confined in the composite particle. And there are two types of the cake, which is the up type and down type. The up type cake that has a 3/3 electric charge, and down type cakes have 1/3 electric charge, and there are up charm and top and the down to one general bottom cake as is generations of the mass ordering. And also other charge, another need electric charge, like the hypercharge and the some of the ice spin, such as the you want to charge also same with the you want the up and down type. And the leptons does not have the color charge, so it does not interact via the gluons and through interaction. But the leptons that has this weak charge, so it can be converted between the charged leptons and the neutrino, which is the neutral lepton. And such as the very well-known examples of the charged leptons are the electrons, anion and tau. Neutrinos that has only the weak charge, so it is only interact via the double uncharged boson. So it's very hard to detect. So neutrino, electron neutrino, muon neutrino, and tau neutrino is corresponding to the each leptons, each charged lepton. And there's a vector P, so-called gauge boson. And such a gauge bosons corresponding to each charge, U1 is 3 charge. And such a U1 times related to electroweak smart with brokens, and the double uncharged bosons coupling to the Higgs, so they are a cardinal mass, and such a mass of double uncharged bosons make the very weak strength of the interactions, so-called Fermi constant. Because the propagators, there are some of the mass of double uncharged bosons in the denominators, and it's a plus of the strength of the interaction. And such as gamma photons still massless, and it can be interact with a very long distance, and it is represented with the Coulomb's law. So well-known laws in the electrodynamics. In that case, laws coming from the such as the massless photons to QD. And they such as weak interactions because of the mass of the double bosons. Its potential is Ricard potential, which is the applied to the only short line distance. On the QSD case, there's still mass loss, but the potential is just as significantly different. There are some of the colored confinements and asymptotic freezing property. So such a gluons through only occurs around very short lines. And there are some diagrams of the interactions between this color spinets and vector P. For the color P, it is self-interaction via the color potentials, the pi photon, and such a spinner. There are no self-interaction, but the Dirac equation represented sort of this propagation. Also, vector fields is propagated satisfying the Maxwell's equation. And the interaction between the scalars and spinor is radial coupling, and the interaction between the scalar fields and the vector fields via the covariant derivatives, and the interaction between the spinors and vector fields via the liquid gauge interaction. And if we know the Lagrangian, so we can obtain the sum of the probability amplitudes, which is the probability from the initial state to the final state. And using the time-dependent motivation, The series expansions of the exponentials of the Lagrangians is coming from the phase boxes or time evolutions of boxes in the quantum mechanics. And we can define the scattering matrix from the minus infinity to infinity. And we can obtain the invariance and amplitudes from the such scattering matrix. And there are some of the Lagrange invariance boxes and the moment contributions boxes will be the contains and that is called the Lagrange invariance phase points. And from that, we can calculate sort of the probability amplitudes or Axon matrix from the Feynman diagrams. There are the series of the Feynman diagrams with the loop diagram. Such a Feynman diagrams contains sort of the vertex or external line and internal lines, and we can calculate sort of the Axon matrix sort of the each component of the Feynman diagrams, and it contributes to the Axon matrix. For example, vertex contributes to the coupling, external lines. As some of the previous and internal lines are the propagated. And such as matrix is still probability amplitude, so we need the scales, and there are just some all possible states as a phase space. And such a phase space has the Lagrange invariance for any objects in any prime. So if the scales, if we scale as matrix and integrate over such Lagrange invariant phase space, then we can assign an observable quantity, which is decay light, over the lifetime through the cross section interacting, effectively interacting area. That's the observable quantity, and we can assign, we can observe such a cross section decay light as a function of the angles or energy. And there are such relations of the cross sections or the decay light with the scattering matrices called the Fermi's golden rule, that we discussed in the previous video. So that was some of the overviews of the particle physics, and there are some of the various approach to the explains of the unexplained phenomena, which is called the beyond standard model.